Hello and welcome to Module 17 of a course called Coding for Crosswords. If you'd like information on the full course, please see the links below. We're in the final stretch now. We are ready to complete this crossword. Remember, it's the dog-cat crossword. And if we look at what we did last time, we are at 400 lines now of file. Boy, that's a lot. We have a routine that we need now, which is to write a word to the grid. So this is when we're deciding to take one of the word possibilities and commit it to the grid. So we're using this word commit to mean that we're going to sort of temporarily put that word into the grid. Let's remember what we did last time. Let's compile the code from last time. It's the same as before, this command line. You have to use the command line for your environment. And if you want any background on any of this, please go back and see many of the previous modules. If we run this, here's what it's doing. It's reading this grid from the file that we define. It has the dog and the cat in it, and it matches the grid that we talked about. And it finds all the spans, and then it categorizes the spans as either being empty, partially full, or fully full. And the ones that we care about are the partial full ones. We can't do any work with the full ones, and we don't really want to work on the empty ones because there's too many choices. If it's completely empty, it means any word in the library that has that length will fit. And that's just too broad. We want something that has already a few letters put in there, and we want to fill in the other letters with viable words. And valuable, I guess. So here we completed all of the solutions for this one slot just for an illustration of what we're doing. Date, data, does, days. And these are the words that are only in the top 12,000 words in the English language. So imagine when you get to using a library of like 200,000, or some of the libraries on the web you can find are 500,000 words. You'll find hundreds and thousands of words that might complete this same pattern. That opens another problem, which I'll talk about in the advanced modules, about how do you prioritize the library words. You have to give them some point scores and let the computer rank some of the choices it's making. But for now, we're just going to try all these words. So let's go look at the code we want. Let's go to the grid class. This is the bottom of the grid class. I'll go to the top of it. And there's a routine we wrote called getString. Okay, it's right here. It is part of the grid. The grid class is here. And what we want now is a routine just like that, only it's going to be WriteString. Okay, and what's it going to take? Well, it's going to take one of these spans, the same as before, a description of where to write the word, and then it's going to take the actual word. So you could pass these in as spans and strings or as references to them. References to them is a little more standard. So there we go. Does it need to return anything? I don't think so. I think it either succeeds if the span is correct and it writes the string, or it just is going to fatal if it doesn't. If the span is for some reason outside the grid, we will fatal. And this will be the first challenge then, is see if you can write that. It'll look a lot like this. You can use this as the template. It's going to be, instead of reading from every box in the span, it's going to be writing to the box in the span. Oh, I made one mistake here. We can't call this S. We have to call this something else. You call it T, or you can call it something better, like Word maybe. Word we're kind of using for the library though. So give that a try if you'd like, and I'll give you some hints next. So here are the hints. First of all, we want to catch the length of the span. And we need to make sure that the word is the same length as the span, right? You can't be trying to write a word that doesn't fit in this span. So this is an assert that we need to put in there just to make sure that we're doing a legal attempt. Then let's do this same type of loop. In fact, we're going to take this same exact loop, including that first line. Right? It's going to be just like this. We're going to walk along every point in the span. We're going to get the point. This will also check to make sure that that point is legal for the span. Get the point. Actually, I think we have to check that separately. Let's check that we're in bounds. So let's assert that we're in bounds on that point, so that the span is inside the grid. Does that give you a hint to go? If you haven't written the rest of it, please give it a try now. You can do it. And if you're back, let's break that into one more subroutine. We have this routine up here that we wrote before called box. We'd actually like to do a similar routine called write box. And I'm doing these lowercase because it's kind of a small routine. You can make that uppercase too if you'd like. What this is going to also do, it's kind of similar to the string case, only it's only a single letter, right? So it's going to take a single letter. We're going to assert that that point is in bounds. And then we're going to say, instead of returning the lines here, we're going to write it like that. Do you think that'll work? So we're writing the box to this point. We're writing this value. This is how we dig the row out of the lines, and then how we dig the character out of that line, and then we assign C to it. If this is difficult for you, please jump back to the module before when we wrote this routine about picking things out of the grid. I'm forgetting which module it is, but it's a couple modules ago. And you'll see how we wrote this code. We talk about that in more detail. But for now, that should work. The write box gives us the idea now of how to write a single character. And let's go back to the WriteString case. And we're going to do something in here that's going to write box, right? We're going to write some kind of box. Now, what are we going to write? Well, we're going to write T is the thing we're writing. T what? T sub I. Okay, we're going to write T sub I, but we're going to write it where? At point P. So that's looking close. In fact, we can take this assert out. We had the write box already checks that for us. It might be as simple as that. Let's just think about that a minute. Now, is this a const function? No, definitely not. We're really writing, this write box is not a const function. Let me make sure I didn't make that const. Right, so this is not const. If you made this const, it won't compile because it'll say you cannot assign to this lines. The compiler will prevent that. So let's go back to the write box here. I think that's good. The length is the length of the span, whether it's horizontal or vertical. We're going to walk over every box in the span, whether it's horizontal or vertical, we don't care. It grabs the point out of the ith point out of the span, and then it writes the box there. So let's do a little test of that. Before we run the whole loop, let's run a small test. Let's do it in here. Commit slot. Right, so we're saying we have all these words to do. Right in here, let's do it. Let's call it test write. Okay, and let's do, what is that called again? It's called WriteString, and it's on the grid. So we need to, that's going to be, in this solver, we've got that as grid, and it's a pointer, so we'll do like that, right? We're going to write the string. What do we have to do? We have to write it to a particular span, and the span, remember we are going over these slots. So if you don't remember this, please look at the previous lecture, but what we're doing is we decided to commit this slot. Out of all the partial slots we found up here, we've picked one, it's just the first one, and we're committing that slot. So this slot, if we go back and look at what that slot has, it has two things. It has a span where it is, and it has the pattern that we're writing, okay? Now, it's not the pattern that we're looking for. This would be like the D blank, blank, blank. We don't want to write that. We want to write the actual word. So what we want to write is, okay, so let's do it step by step. First, it's the span. So it's going to be slot, span. That's where we write it. And then the word that we're writing is actually going to be this word. And the word that we're writing, you get it like this. And then let's, new grid is, and then let's print it, okay? So that's going to be grid, print. So let's see if that compiles. And let's find out what we did wrong. It can't find this W. Okay, I see. So, right. So here I looped over all the words. There definitely are words. And then I looped over all of them. And then I went ahead and I forgot W was only valid in here. So I tried to use W here. And W is not what we really want. Let's do a couple things. Let's assert, first of all, that the words is not empty, right? It's a little bit of a subtle point, but the words pointer could exist, and it could point to an empty list. We don't have that case, I don't believe, but let's just make sure with the assert. So again, this is a case of using asserts to guarantee that you're not doing something wrong. Sorry, we want to assert that the list is not empty, so it has something in it. And then let's do one word. It has to be a const word. We can call this WW or something. It's the word we're going to write. Oh, we can just still call it W. Equals words. It'll be the first word. It'll be 0. And this is an example where, again, it's a C++ thing. Words, remember, words is a pointer. It's a little tricky. We've made words as the vector itself, and then we've made this routine return either null or a pointer to the words. So to get at the actual words vector, we have to do this dereference operator because words is a pointer. So because of this pointer here on words, we need this pointer here, this dereference operator, to get to the actual vector again. So those just kind of go hand in hand. So you need this to get at the 0th word. So we're going to write the 0th word. So that will give us a W then, where we can then write the word there. In fact, let's test write. Let's say what we're writing. Test write of. Right. Let's do like that. Right. And let's see if that compiles. And it does, and let's run it. And here we go. So now this is interesting. So we got the original grid here. We found the different stats. We've got all these possible completions. And then now we're doing a test write of what? Date, because date was the very first word. We just picked that because we said right up here back in the code, we just picked this 0 arbitrarily, right? We could have picked word 13 if we wanted, and then it would have been, dead or something. But we picked word 0, which is date, and then we wrote it to the grid, and then we printed the grid out. Now look at this grid. Isn't this great? This is just what we want. We want to see dog going this way, and we want to see date going that way. So you get the idea now that if we were to run our routine again on this and find all the spans in this routine, you're going to see it's going to find dog, and that's going to find A blank blank, T blank blank blank. So it's going to find many more partial spans now, which are kind of interesting and can have words put in them. So we're closer. The big thing that we need, the tool that we need right now, is something called recursion. And so I'm going to write a very small example of that, a little bit separate from this other stuff. Let's just go back to main, way down here in main. Let's just even comment all of that stuff out. Okay, this is going to be just a very simple example way up here. We're going to call a routine called foo, and I'm going to call it with 0. And what am I going to make foo do? Foo is going to be a void function, and it's going to take an integer as an argument. Okay, that's it. We can even print out foo, and then we can print out what I is, okay? So first, let me just run that, just to give you an idea of what we're doing. That's just a very simple. So there, foo 0, right? What were to happen if we did this? What were to happen if we were to call foo again? And let's call it again with something different. Let's call it I plus 1. Okay. What do you think is going to happen? I'm not going to run it because that actually is going to hang the process, because it will run infinitely. You can try it in your environment if you're gutsy enough. It will run recursively forever because it keeps calling foo over and over again. So let's do something else. Let's say if, how about this? If I is less than 5, then let's call it, right? So every time we call foo, we're adding 1. So it's going to go 1, 2, 3, 4. And then when it hits 5, when it finally calls 5, it's going to print foo 5. And then it's going to say, is I less than 5? No. And then it's going to just come back here and it's going to return. And then what's it going to do? It's going to have to return all the way out of 5 of those foos. So what I expect this to print is foo 0, foo 1, foo 2, all the way up to foo 5. And then it will return. So let's see if that, and this is a good exercise for you to try before we try it here. And there we go. So you see it's doing the recursion. It's a limited recursion, and that's what we want for our loop. We're going to call the loop again in a limited recursion way. And so let's put it all together now. Let me get rid of this stuff. That was just to show you the idea of how you can call a routine from within itself. So this is kind of strange, right? We're calling foo from inside foo. You know, that you might think that that would be illegal, but it's not. It'll do it. It's just you want to be careful to only do that in a terminated way. So let me get rid of that code and then that code and put this all back. And let's go back up to this commit slot. I also want to make one change. I think passing a pointer into solver probably maybe a little confusing. So I'm going to just get rid of that. I think we can do this without the grid pointer. And keeping away from pointers is a little nicer, just for not confusing people. The code looks a little more like Java if you don't use pointers anyway, which is a little more general. So let's get rid of that pointer. Let's instead put a reference. Let's put a const reference to the grid when we call the solver, okay? And then that means in the solver, we're going to have a grid. It's going to be a reference now, so you just do like that. And then when you call the loop, we want to actually pass that grid into the loop. So here's what the loop is going to need. And the loop, and this is going to be the trick, the loop is going to take not a reference to a grid, but an actual copy of the grid. So this is not a reference on purpose because we want every call to loop to get a new copy of the grid. And that's important because as you recurse, you might get to a point, well, you will get to a point when you can't go any further. And what you need to do at that point is back up. And when you back up, you want to throw away the copy of the grid that you tried, and you want to go back to a previous copy of the grid. So the fact that this is not a reference is critical to the functionality of this whole thing. So make sure you understand that. If you make a reference, it's just copying in a way of referring to the object that you called from. If you do like this without a reference, it's making a full copy of that grid object. So all that stuff in a grid that's in the private data, I'll go to the bottom of the grid structure, all this stuff that's part of a grid, when you copy a grid, this will all be copied. It'll make a copy of the name, a copy of all those lines, a copy of all the spans. So that's kind of inefficient, but it's a way of preserving a whole copy of it. Then we can mess around with writing that, and then when we're done with it, we can just throw it away and jump back to the caller. Okay, so let's go back up to the solve routine here. Let's get rid of this grid then. Anywhere we're calling grid underscore, we're going to get rid of it. So in the loop function now, this grid becomes, instead of a pointer, it's just back to a regular. So let's do it this way. Let's look for any more of those. Right, I think that's it. Grid underscore, so the grid underscore is gone. Okay, so I just changed that back to be just a regular grid. So here's what we're going to do. Commit slot is going to also need to take a copy of the grid. This may or may not be const. Let me think about that a little bit. And this one actually can be a reference. We only really need one copy per loop. You know, we don't need to make a new copy of the grid every time we pass it into a routine like commit slot, which is just called from up here. That can be, this grid can actually just be referring to this one up here, I believe. We'll see that in a second if that's true or not. So here we go. So we're going to keep this the same. We're finding all the spans. We categorize them. We find out which ones are partial. Okay. And then we come down here to the commit slot. We decided to commit this slot of this grid. So in commit slot, since we've added this grid argument now, we're passing the argument along instead of having it be part of the class, the grid class. We need to also pass it here on the call to commit slot. So we compute the stats, we find the one slot that we want to commit, and then we commit that slot, and in that slot we have all these words that we want to commit. Let's just commit the first word, and rather than doing this, let me see. Well, we can actually leave all this, and we'll always commit the first word, and then at the bottom here, what we're going to do, we're going to print it. Here we're going to do, this is the whole key of this module. So we call loop with grid, and because the declaration of loop up here it takes a full grid, that will make a copy of the grid. Let's do one more thing, like we did for our little test recursion. Let's add in a thing called depth here. When we first call loop, let's put the depth 0. Every time we call loop, let's add 1 to the depth. And let's do something special just to sort of bound things and make sure this doesn't go crazy on us. Let's say if the depth is greater than, let's do it 3 times, okay? Then we're going to return. What this does is it makes sure that we don't call this thing forever. But we got to pass this depth in now. So when we come down here and we come to commit slot, we also have to add the depth here. And we have to have it in the arguments to commit slot. Why do we have to do that? Because we have to pass that all the way in so that when we call loop again here, we can pass that depth in again. So we're kind of carrying it along with us in these arguments. It goes into the loop function, and it goes into the commit slot here, and then it goes into commit slot, comes into commit slot here, and then it goes back into the loop again here. Now, of course, if we find no matches, we just stop here. No matches to the pattern, and then we exit. So what we're going to do is run this. First of all, let's see if it'll compile. That was a lot of code. It might not even compile, and it didn't. Let's fix that first. So 445, and my code is right here. Oh, so I don't need this ampersand anymore. So that's part of that cleanup. So actually don't even need the grid at all because we're going to put it in here instead, grid. Right, so we're no longer making the constructor take a grid. We're just going to pass the grid into the actual solve function, right? Okay, that should clean up that first thing. Let's see what other errors there are. Oh, that was it. Okay, so now we're going to run it. Now what's going to happen? We hope that it's going to run loop 3 times. So it might be a lot that's going to happen here, but let's try to figure it out. Here it goes. Let's do it step by step. Let's scroll back up to the top. So here we go. Here's the spans. It should call that just once because those are going to stay the same the entire time. It reads the library. That's fine. It prints the original grid, which we're well familiar with by now. It counts that there's 6 empty, 6 partial, 2 full. It picks the first partial, which is this D, which we did before. It's going to pick date. It's going to write date in, which it did right here, which is great. Now this is the new stuff. I called grid again. Now this time there's 3 empty and 8 partial because you see it took away 1 partial and made it full. So there's 3 full now, but it added 3 more partials. So that results in the partials going up by 2. There used to be 6 partials, now there's 8. And that's what this shows. So there's 8 things, 8 more slots that we have to work on. The first one of those happens to be A dash dash. You see where that is in the grid? That's right here. So the next word that we're going to try to commit is to find all the words that fit right in here. And that's going to be all the possible word choices that have A blank blank. And that's all of these here. Now, again, we're just picking the very first one, and, happens to be and here we go. We're going to write it. We're going to write and. So there we go. Do you see where it is? Right there. Now, you can already tell the problem. We're already developing a pattern GD blank blank. That's going to be hard to match, but we haven't got to that yet. The next pattern that it finds is this one across, T blank blank blank. Okay, that one. Now, that's got all these possible matches, which looks pretty good. And it goes ahead and it writes it in. And now at that point, we should print our depth because I think our depth is what's keeping us here. So let's go back to the loop and let's write that in. Let's say aborting the loop because depth equals depth, okay? Let's just run that and make sure that the reason we're aborting and not writing more words is because of this loop. And there we go. So you can see that. So aborting loop because depth equals 4. So we did in fact hit this case. Let's go a little further though. Let's go another couple. Let's go to 6. Let's see what 6 does, okay? Let's compile that and let's run it. This is gonna be a lot more stuff, but here we go. It did date, it did and, it wrote that, and now what's the next one it's gonna find? Oh, here we go, E. Right, so we wrote that was the last thing that we wrote, that went right across here, and then it says partial. There's 7 more slots that are partial. The first one that it picks in that list of 7 is this one, E blank blank blank, and then it said no possible matches. So I actually had to stop and go debug that. Stop the video because I didn't expect that. There's a bug that I'll explain that caused that, and it's an off by 1 bug. And off by 1 bugs are the bane of computer programming. And here's where the bug is. You wouldn't be able to guess this. When I did the max size, remember we back a long time ago we filtered off the library so that it would only, in this case, read words up to 7 length. And look at the code I did to do that. It's right here. If the length is less than or equal to max size, so this is going to be 7 because the grid is 7 by 7. If the length of the word is 7 or less, then we put it in the hash table. Now, in fact, 7-letter words are not making it into the hash table. That's the bug. And it's kind of dumb because here's the thing. Here's what it is. Remember this DOS end of line problem? I stripped off this last character in some cases. I'm reading a DOS file for the words on a Unix platform. And this will happen if you're on a Mac too. And so I removed that character here. But look, I've computed this length up here before I did that trim. So I'm actually off by 1. It's thinking that a 7-letter word is only 6 letters long. No, rather around. It's thinking that a 7-letter word is 8 letters, and so it doesn't put it in the hash table. So instead of length here, I really need to go back and recompute the size of the line. So I have to go line.length here, and that'll get rid of that problem. Okay, so that was a problem that you probably won't have if you're running on Windows or in a browser reading the you won't hit this DOS end of line problem. Anyway, that's just a little diversion, so don't let that detract from the lecture. Let's go back here and recompile that, and then I'll go back and run. Okay, now this will come to something more interesting. Here we go. Let's follow this through back from the top. So here we go. Here it's writing date. It writes the next word, which is going to be and, like we did before. So here it's going. It's dog and it writes that next, T-H-A-T. Now already we're in trouble. O-N-H-G-D-A. Those are not likely to be words. But here's what it hits. By the way, this time we did get this 7-letter words in there. So here's all the possible 7-letter words. A lot of great words. These would be fun for a crossword, right? I mean, if you're doing a crossword for your friends or to publish, some of these would be kind of fun. You know, emerald maybe would be nice. Some words are kind of more, like elastic is kind of a fun word. Some words are just more interesting than other words, and that's up to your discretion, of course. But the whole idea of this program is just to give you ideas. You know, it's to present different solutions, and then you can pick which ones to pick. So here we go. So it wrote in English, and now it's coming to a slot that says TL dash. And that's going to be this slot here. Do you see it? TL dash. It's that very middle vertical slot. And that slot, now it goes to look up options for that slot. Even though it actually was already in a dead end here, we didn't detect that yet. It dead ends now because it says, look, there's no matches to that pattern. So are we done? I mean, does that mean that there's no solution to this crossword puzzle? There's no way to construct this crossword puzzle? Well, no, because we've only tried the very first possible word in all those word choices. So what we want to do is go back up now and try other words. But there's a more fundamental problem we have to fix before we do that. So we'll do that in just a minute. But the more fundamental problem is that when we wrote that English in, look at what happened. We saw this blank here, and we looked at all the possible words, but we did not consider how when we wrote in English into this spot, it completed these words. So what was previously a partial slot, O-N-H blank, G-D-A blank, really what we should do at that point, before we even go and try and look for other slots to fill in, like TL blank, we really need to check all those words, and we need to say, look, that's already not a word in the English language, not a word in our dictionary of 12,000 words. So we need to check for that, and there's different ways to do it. You know, if you're going to be doing it more optimally, which I talk about in the advanced section of this class, you can do it right in here when we write the string. You know, when we do the commit word, there's a way you can actually, when you're committing this slot and you're writing that string right into the graph, you can actually look and see if there's any of the cross spans that you're completing. And if you're writing the last letter in to a cross span, you can, right then, you can say, look, we're done, you know, if it doesn't make a word. Or if it makes a word, you can keep going. We don't need to be that optimal for this code. So what we're going to do instead is just at the start of every loop, look back up here. We already kind of have this structure set up for this. We've already made a list of all the slots that are full slots. So what we can do is, before we even start to do the commit slot here, let's check, even before we check to see if we have a solution, because we don't want to give a solution if this fails. Let's need to check that all words so far are valid. Okay, so this is a piece of code that we have to write here. So that's your next big challenge, and we'll work through it. How are you going to check that all those words are valid, that you've happened to have completed with all the crosswords? And I'll give you a hint now. And the hint is that we've already collected all those slots here. So we've got them collected right here with the patterns in each one of them. And the pattern in this case for the full slots is going to be the complete word. So you want to iterate over those and then check them against the library. All right, so if you're back, let's see how you did that. It's going to really be this pretty simple. It's going to say const slot reference on the full slots. I think that's going to be fine. That part looks fine. We should be able to do that. Because we're coming in here with the grid, we're computing the slots, just making sure that this will be okay. We haven't used this variable s for something else. I tend to use these small variables. Some people might, you could write a whole thing here saying, slot under consideration, something like that. People do all kinds of long words. I just like the way this looks. Just the only danger of that is that you have to make sure that you didn't use s for something else up earlier. So what are we doing here? Well, let's just write this first. We can just write a little routine that says checking, and then what's it going to be? S. It's a thing called pattern, right? If you didn't remember that, let's go back up and look. So I'm going to jump back up and look at the slot, and there's a thing called pattern. We stored the pattern in there. Remember, we got the string from the grid with its span, and then we stored it. We stored that pattern. So that's here, and we're going to print it out. I just want to show you what we're going to be doing. Checking pattern if it is a word, and then let's do the check, and let's check against the library. Remember, we have our library, it's just called lib. And what is the routine in the library? I think it's just called find word, right? So it's just find word. Whether that returns null or not. It's actually returning a whole list of words because we're using this find word for really all the patterns also. But we can also just use it for the completed word too. Oh, I think actually, wait, we have another one called isWord. That's already a little bit more specialized. Let's use that one instead. We could call find word and then check to see if it returns a null pointer or not. But we've already got this one that we wrote earlier. So let's just go ahead and use that. Let's say isWord string. Okay, so let's go back to our loop function, which is here. Okay, so we were working on code right in here. We're going to say lib isWord was what it was called, and we're going to check against s pattern. So if it is not a word, let's print not abort. Okay, we'll remove some of these prints once we get this thing running. It's gonna do millions of searches here. We want to get rid of all these prints. But just for now, when we're running just a little bit, you can see what this does. So this should catch. If you go back to what we ran last time when it wrote this English and then it even tried to get in here and check for the TL, we shouldn't even get this far. It should write the English, then it should call it again, and before it even does this commit slot of the TL, it should fail, and it should say what? Like maybe ONHN is not a word, I think, is what it probably will say. So let's compile that. Let's first of all see if I did it right. Okay, that worked. And let's run it. And let's walk through this slowly. Let's go back to the very top again. Here we go. Okay, this is the original stuff. It's just finding all the spans, which again stay the same. The geometry stays the same the whole time. We read all these words. Oh, it's reading a few more now because we fixed that off by one bug. Used to be 6,000, now it's 7,000. Here's the original grid, the original check of in the loop. And then now we're going to check dog and cat, and that passes, so that's fine. So dog and cat are words already. And then we write in date. And then again, we're checking to see that dog, cat, and date now are words. That's fine. Then we write in the and. Okay, and it doesn't check these yet because there's still some blanks on them. They're not fully done. So it checks these. Those are all words, and that's fine. Then it writes in that, which is here. And now it still checks to see all these are words, and that's all fine. And then it checks, it writes English in. Oh, I can already see a bug we did. But here, let's keep going. Okay, so here we go. Checking, yeah, it checks that one. Where'd it get the ONHN from? Well, that's from this vertical one here. ONHN, right? Abort. And then check GDAG, and it says GDAG is not a word. Abort. But then guess what I do? Look, I'm going to commit the slot anyway. You know what I forgot to do? Can you see? If you go back to the code, I checked to see if they were words, but I didn't do anything. I kept going. I really wanted to do here. I wanted to do a return, right? I wanted to do something to just get out of here. I think a return is fine. I think this return, we don't return anything, right? It's a void function. So at any point in the loop, you know, like we did here with the depth being too big, these recursions often have an easy out. Anybody who wants to just end the recursion can just return, and it'll just call back up the stack again. So anytime we hit any kind of problem where we say, hey, we don't want to keep going down this path, this looks like a dead end path, we can just return like this. So if we return, let's just rerun that just to make sure that It's doing what I claim. Then at the very bottom, I won't walk through the whole thing again, but at the very bottom, it writes English in, right? So here's the write of English, and then it writes English in, and then it checks all these things, and then it says, ONHN is not an abort. And right then it comes out. It doesn't even check the GDAG. Okay, so we're getting a lot closer now, and I'm wondering how we should do this in a way that will not be everything at once, you know? So we're kind of in a, I almost have to turn on the whole thing and then you're gonna get the entire result at once. Let me try to creep up on it some more though. Maybe we make the depth a little bit bigger. So instead of 8, let's go maybe let's go to, instead of 6, let's go to 8. But I think it's still gonna abort right there and come right back again. So I think if we run this, it'll do the same thing because it's gonna hit to the same level and it's gonna abort again. So what we really need to do, I think finally we need to really just turn it on. So instead of here, you see, this is the part right here where we're, right here in the commit slot routine. We're always picking the first slot, that's okay. But when we pick the first slot to work on, we're only gonna return here, we're only gonna dive in on the very first word. So this is what we have to fix. So let's go ahead and jump in. This is gonna produce probably 1 million lines of output, but let's just do it. We still have that depth that's gonna limit us, so it won't be terribly deep. In fact, let's put the depth back. Let's put that limit on the depth back to something like 5, so it's pretty small. And then let's go ahead and turn on though the full look at all the words. So here we go. So here's all the words. Instead of just calling it on the first word, let's go back and put this assert here. Actually, we don't even need that assert anymore. We're going to get rid of this even. We're going to put all this stuff inside here. See what I just did? Oops, I did that wrong. These go out. Okay, so here we go. So I want for every word in that word list, you know, and if you look back here, remember these word lists can be pretty big. These can be like, you know, 40, 50, 100 words might match. For every one of those words in that word list, we want to do this complete, oh yeah, we don't want this W anymore. We want that W, we want this gone. We don't want to pick 0 all the time. We want to pick that word in the word list. And let's get rid of this line too. So we're going to say it's no longer a test. We are, let's call it committing this word, okay? And then we're going to write it. Then we're going to make a new grid. We print, let's still print it. And then we're going to call loop again on it. Okay, let's give this a try. This could possibly result in a lot of output, but let's see. So first of all, does it compile? Yes. Okay, let's run it. Here goes. And look at that go. Okay, so it's a little crazy. It is trying a lot. You know, wait, let's go back and change the depth. This is what I was a little afraid of. It's a little hard to show this without showing everything. Let's put the depth, oh, I don't know, let's say even 2. Let's see what it does with just going to a depth of 2. Let's clear this and let's run it. And that does stop, okay. Let me put it into a file. On this system, I could do it like this. Ooh, it's 30,000 lines. So even going depth of 2, it goes 30,000 lines deep. Okay, let's try to look at what it's doing. I can't scroll through all this, of course, but I can show you at least part of it. So here we go. Okay, it wrote date. Okay. It wrote and. It wrote are. Let me search for this committing word. So committing any, it wrote any. Oh, it's trying different words in here because it keeps getting stuck when it keeps writing. Oh, that's the depth equals 2, actually. That's the depth equals 2 kicking in. It's not letting it write more than 2 words. So it's writing all the different words, dog, eagle. So look at all the words it's writing. I keep searching to hit the next one of these. It's writing all the different options in there. And there's a lot of them. Right. Okay, so here's what it's doing. If you look at the list of words that it can write, there are something like 50 maybe words with the D blank blank blank, and there are something like 50 words with the A blank blank blank. It is trying all 50 times 50 combinations of those words. So it is trying grids that have 2,500 different words in it. And each one's printing out, you know, about 10 lines. And that's why we're getting a file that's like 30,000 lines long. So that's why we're printing this out. Look at what it's doing. It's trying all this stuff like UFO, UPC. So for every word down that it picks, it's trying all 50 of the different across words. And that's what we want. We want this thing to look very comprehensively. Let's change it to depth greater than 3. Let's see if that will give us something. And away we go. And there it goes. Boy, it really prints a lot. So that even just 3, it prints an awful lot. So we need to not print so much. So let's go ahead at this point and let's look for where we say solution. What do we want to do in the solution? Well, I think what we want to do clearly is to print the grid. So we're going to do this solution and we're going to print the grid. So that print we want to leave. But we want to basically return, we're going to comment out all these other prints. We just have too much, there's just too much stuff here. So let's look at where we're printing everything and let's comment this out. And let's also make this a lot bigger. Like we could make this, actually we can even comment this whole section out. Let's just let it go now. Let's turn it loose, okay? But let's take all the other prints out. So we can, that print we want to leave, that's part of the solution. But all this stuff let's take out. Committing word, and then this print let's take out. So nothing I'm doing here is functional. I'm just removing all the print. So we should be able to at least run without having it print so much. So let's give it a try, and let's see if it only prints the solutions. So here we go. This is the big aha moment of the entire lecture series. And there we go. Oh, we still have no matches to patterns. Let's remove that. That's right here. Let's print that out. So let's comment that out, I mean. Okay, here we go. And there's the original grid that it prints. And now it's just grinding. And I didn't compile as optimized, so it might be a little slow. It's copying all those grids back and forth constantly. And it's grinding, and it's grinding, and it's grinding. So let's do one thing, because this needs a faster compile. The compile command we've been doing is this. Depending on your environment, this may change, but in this environment, I can do what's called O2, which will optimize the program. We haven't needed to do this yet because we've been running small enough programs. This is a large enough program now. I mean, it's doing enough computation that we need to compile it optimized. So let's compile it optimized first, then let's run it, and let's let it go. Now, we have to wait a little bit here for it to run. And there we go. It finished. And look, it found a solution. Solution, my grid. So look, it found something. So look, dog, ISO, that's probably a standards organization, I guess, or in search of, maybe on a want ad. Slam, columns, dice, sand, cat. Sand be like San Francisco. So look the other way. Dice, disc, Oslo, goal, mud, misc, NCAA, and then cent. So those are all words. So this is a valid grid. So this is really great. And none of the words are duplicate. But look, we have this error here. And I can explain that one. Jump back up here. That's a simple bug. We look for the solution. We sort of say, hey, are there any more slots that are either empty or partially empty? And if not, we say that's the solution. Then we print it. But then we keep going. This really needs to be a return right here. We're done. We're done with this whole... this is all a what-if thing. We're trying all these different paths of searching the combinations. And if we got to this point, we print it out, we're done. We can't keep searching. There's no more things to search, right? We're done with all the slots, so we have to return here. So when I do that, we'll probably end up with more solutions. So let's try that. This will be interesting to see how many solutions we get. And I think when I ran this before, I got 13, but let's see if that's still true. So there we go. Here's some different solutions. Look at these. Flag, folders, prop. Oh, so instead of prop, it's now prep, cat, spot, and that's it. So there are at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh yeah, I think it's something like 13. Let's put it into a file, and then I can just search it. So then I can do this thing called grep. In Linux, that's a command that searches for things. I can grep for solution, and we can see how many solutions it finds. And let's actually word count that. So it's 14. So it found 14 solutions. And here they all are. So there's one. So here they go. Yeah, so it's kind of cute. So these are all different solutions to that puzzle. Here's one with tire, C, res. And so now the fun begins. There's one more homework we have to do, which I'll do in the next lecture, which is to detect duplicates. We're not doing anything yet to guarantee that there are not duplicates in this. And crossword puzzle rules require that there not be any duplicate words. So we really need to do that. So that's going to be a little bit of a separate task. And then after that, we can just play with it. So there'll be one more module in this course when we'll try to detect duplicates. And we'll do that one. I hope to see you there. And then we'll be done with the entire basics part of the Coding for Crosswords course.